We are open for discussion. I mean, not just on these two talks. Of course, they're the sort of the starting points for a broader discussion. We have about 40 minutes total. We'll try to wrap up on time. So, any questions?
This is in reference to Marcus's talk. I said I have a bone to pick with him, and we're going to do it in public. So, first of all, that's fantastic. I really like the way you laid out, perhaps very strictly, the numerical requirements. But I think that's right on target, right? And both at ILAS and other places, I know that both of us have been very keen on seeing that kind of convergence demonstrated. The one thing I do want to say is that you mentioned Lagrangian Eulerian calculations. And I completely agree with you that everything you have seen in most of the simulations are subject to the inconsistency of mushing up modeling and numerical errors you talked about. But not to toot our own horn, but we'd learned something from the same problem occurs in single phase flows when you do PDF methods with Monte Carlo simulation of particles. And there it was shown that you can use what's called a grid-free kernel. And the kernel is tied to a physical scale, right? And we adapted that method and showed that the Lagrangian method actually works, and it will give you exactly fantastic convergence. And all that is published in International Journal Multiphase Flow, two articles I can send to you. So I just want to tell people that the LE method is very powerful, and it's a good method, and there is no intrinsic limitation from the theoretical viewpoint to that this grid size getting tied to the particle size. That's completely an artifact through, I would just say, early implementations that didn't recognize this point. I just want to make sure that people don't run away from the method for the wrong reason. Fair enough.
And
Speechless.
no, okay, I completely agree. And that comment about Eulerian Lagrangian simulations was much more targeted towards the approaches that are currently in use in industry and these early simplistic type of implementations of it. And I just wanted to point out that they have to be done in a better, more consistent way. And yes, there are ways of doing it, right? And many of the things I talked about, there are pockets of people that know how to do it and do it. It just has to be applied much more broadly and brought to the thing. So I completely agree. That's exactly it.
Any other questions on the two talks specifically? I have, just as, yeah, go ahead. Thank you.
Marcus was talking about continuum limit. When you hit the continuum limit, how to actually deal with simulations, how to actually make them more accurate. So there are some studies which are coming up now, which talk about sort of a multi-scale simulation. So what you do is, when you go to molecular scale, you do molecular dynamics, then you couple it with the continuum scale, and you kind of resolve that issue of having multiple scales there. But the only issue that is currently kind of hindering that kind of a study is that it's not just multi-length scale. Whenever you talk about multi-length scale, you always talk about multi-time scale as well. So how to actually couple it in time, because you don't want to run your MD simulations to millisecond or probably even microseconds even. So it takes a huge amount of effort. And so probably, I'm not sure if Marcus would like to comment on it further.
I can try. Yeah, I agree. I mean, I just wanted to point out that there is this issue and it has to be addressed. And yes, molecular type simulation and trying to couple them is one way, which opens the length scale and the time scale coupling issues. And we probably have to look at, I mean, it's not the only place where there's these difference in time and length scales and how to couple them together. That happens in other problems as well. And we just have to look at how can we port these type of ideas over to atomizing flows and really study when does it matter and when does it not matter. But I don't think it has been conclusively shown when it is important and when it isn't. And my intuition is that it is very important in sheet breakups and not so much in ligament breakup. But it's something of a more fundamental study we should look at and trying to combine these type of methods, a more fundamental type of study, so that we can go off and do the full type of atomization simulations and then have some increased level of trust in them.
Another thing is what happens at the contact line at the nozzle. That's another issue. So that also has to be resolved somehow, right?
Yeah, I mean, yes, I agree. And that brings into question all the internal flows in the nozzle as well. And is it all single flows? Is it all liquid? Or do you have cavitation inception? What happens if that interacts with the boundary? What are the contact lines? How does it persist? Does it exit? Does it collapse again? Yes, there's, from a physical point of view, modeling type of thing. Yes, contact angle, the correct treatment of the apparent contact angle and the microscale contact angle. Because typically we could do with Navier-Stokes, we could do the micro contact angle, but then you have an apparent contact angle to treat with. All of these things, when interactions with boundaries or spraying or film formation comes into play in some of these more modern atomizer designs where you have a liquid jet impinging on a wall to form a film, like pre-filming atomizers. How do we deal with that? How do we bring in those types of physics? Are all playgrounds we can try to explore, right. And we'll have to.
So you talked about breaking up sheets where the sheets, because of the shear flows, they keep becoming thinner and thinner, but they never break. They would never break unless until you bring van der Waals force into action. But I believe there are some recent studies by Tryggvason et al. What they do is they look at bubble coalescence effects. So instead of when your bubbles are coalescing, so it greatly depends on how the thin film between the bubble actually is kind of gushes out from the gap. So what they do is they use a thin film model. They're still in the continuum limit, but they're bringing in some microscopic effects like van der Waals force in the continuum limit. And probably something of that sort you can also want to try.
Yeah, and I agree. I mean, those are all avenues we need to, I think, explore. Going full DNS with van der Waals forces would be one brute force way of trying to do it, but we can probably be much smarter about it, bringing in these models, these, I don't want to call it reduced or lower order models,
thin film models?
But for these, yeah, these film models for these specific scenarios where we apply them then only to this specific scenario as well, that could help us improve our simulation results. And I think there's a lot of things we can still look at and try to explore to improve the results.
But there's one more comment, one final comment. You talked about continuum surface tension being dependent on, in some way, actually being mesh dependent. But I believe the CST model, the way it is theoretically, what it says is that as you keep on refining your grid, that surface force becomes even like closer to what it should be like.
Yes, I agree, but that's the same type of arguments that LES people make, right?
Right. Yeah.
If you refine, you come closer to your DNS limit. But that's mixing two things, right? If you have a model parameter, which is the, let's stay CSF, so we look at the gradient of a color function or a volume fraction. So that introduces some type of length scale, right, together with the C. So if you introduce a certain length scale in the way you spread your surface tension force, and then you should keep this constant when you refine your mesh. And there are ways of doing this, and consistent ways of doing this, that are shown to be grid convergence. If you start out with the delta function and use approximations for the delta functions in a certain shape, and they're not the typical delta function shapes. There was a paper, I forgot the authors, that specifically looked at convergent approximations to the delta function, so that you keep that width constant, because that becomes a model parameter at that point. And then you do grid refinement studies and decouple your numerical parameters from that and show that it would converge to an answer that is appropriate for that thickness of the delta function approximation. And then you can go into reducing that and then doing grid refinement again to decouple these modeling errors. And inherently in the CSF, those two are coupled if you just take the gradient of it, which, yes, in the limit of infinite grid resolution approaches the delta function, right? That's the point. But it mixes these two these two type of things, that it is only a good approximation to reality in the infinite grid resolution limit. Right. And if you want to know what the modeling errors is, you would have to decouple the two.
Yeah. And the same thing goes for when you actually look at these methods like interface tracking models, like level set or BF model. You talk about smoothing the properties across, because you have a continuity of the properties at the interface, and you have to smoothen them. So there are various ways of smoothing. You can use what I call weighted arithmetic mean, weighted based on the void fraction field, and there is a weighted harmonic mean that you can also use. And what we have seen is, what we did studies on, we solved electric field equations, basically solving for potential equation for electric field. And what we saw was that depending upon how you actually choose this interpolation function, it can affect your bulk solution as well. Like it kind of comes in when you are solving Poisson equation in terms of flows, two-phase flows. So there your density has to be properly interpolated. So would you like to comment on it?
True, I could try. Yes, you're absolutely right, and that's a big issue. So in our case, what we try to do is we try to formulate it all in a finite volume sense. So there in a finite volume, if you maintain the sharp interface limit, you still have the integration over your cell volume in it, right? So that, okay, you can call it smoothing, but it's a smoothing of, it's the correct way of smoothing in the finite volume sense in this point. But yes, if you do a grid refinement study of that, because you have in a finite volume method the volume integral in it, that integration volume changes. Is that an inappropriate mixing of model and numerical parameters? Probably, maybe, I don't know. There's no way around it at this point unless you don't do a finite volume method, which you probably should do. I mean, the ideal case is that you keep a purely sharp interface method with a grid line at that boundary of the phase interface and then impose the jump conditions there. That would be the consistent non-smearing way. And everything else that uses fixed grid methods typically has one form or another of smearing. You can do smearings with analytical functions of a heavy side that is smeared out, which you could keep the distance constant, right, the thickness of it constant under grid refinement. That would be one way of doing it, but you'd have to do it in such a way that this actually gives you grid converged solutions, that you don't introduce additional errors in it. It's very similar to the delta function approximation, except that here it's a heavy side one. And I agree, those are all things in that continuum limit. When it's a discontinuity, we have to really think about, from a more fundamental point of view, how do we deal with this discontinuity in a consistent, convergent, and stable manner.
Because that also puts a limit on, if you use a single cell method where you have your discontinuity captured in a single cell, then your property is actually going through a big jump there. And depending upon what density ratios you're dealing with, your Poisson equation solution.
Yeah, sure. No, absolutely. And especially in the low Mach number limit, the Poisson equation becomes just so stiff if you have high density ratios. I mean, I didn't touch upon this, but there are, if you use typical level set formulations, there's a lot of because I talked about consistency of methods, right? Level set methods are terrible in some sense, right? Because you can't make them consistent. There's no inherent volume conservation in a level set method. If you try to bring it in, you're switching back, like CLSF-WOF methods, you're essentially switching back to a WOF method with some level set parts to it to make the WOF method easier. But there are all these type of consistency issues in replacing the continuity equation with your interface tracking scheme that then still have to be consistent with the solution of the momentum equations or not. And oftentimes, many methods that we use, that we've used in the past, are not consistent. And that shows up when you go to high density ratio flows with large shear and complex interfaces. So many numerical simulations you're going to see, not only from my group but from others as well, work with low density ratios if you have high shear and complex interfaces. You can do high density ratios, high shear, and simple Kelvin-Helmholtz type instabilities, not much, no problem, or any other of the two combinations. But the combination of the three that causes problem because of inherent inconsistency in the way we replace the governing equation, which is the continuity equation, with our numerical technique that we express in form of a level set method, for example. So a whole lot of issues still to be resolved. I agree.
Just to sort of, I think if I may intervene briefly, what I thought, we just sort of put down about 4 questions, one of which is in red, please don't try to strain your eyes and read the orange, because we'll come to them shortly. We're just sort of looking at our own understanding of atomization as a problem. We started, I mean, none of us in this room are probably responsible for this, but somebody wrote down that there was a primary atomization and a secondary atomization, and that's the original sin we are all living with. And now that we have to resolve it somehow, let's ask ourselves this question: is secondary atomization, at least the way we've come to know of it, single droplet breaking up in a breeze, still important in a real spray? So what I thought we'll do is, over the next half an hour, just briefly run through 4 questions. I'm not too tied to 4. If we get through 2, that's perfectly fine too. Just sort of try to see where our understanding lies on these, both from the experimental and modeling perspective, focusing on the physics of how things work. So, Nicholas, do you want to start off?
But I think that Marcus has shown that it was not the dominant mode of atomization. I think it's secondary atomization. It's like in the name. It's because it's not the dominant mode
Right.
of atomization, but actually the physics is nearly the same.
Okay.
So, but you have a small blobs which can atomize, and you can make primary atomization of a droplet and call it secondary atomization. And I think it's mainly a question of vocabulary rather than physics. The physics behind is nearly the same, as far as I'm concerned.
Well, I think it depends a lot on what we call primary atomization, where we do the switch between primary and secondary atomization. I have my specific way of defining what I call primary atomization when I do transfer into Lagrangian spray drop models. And if I take that as primary atomization, then in my simulations, for the cases at least that I analyze, I see hardly any secondary atomization, even though we have a stochastic secondary atomization model active. And we don't see them because the Weber numbers of the drops are not large enough. Now, it might completely change if you subject this spray then to an auxiliary flow, right? Then you introduce additional shear, you can shoot up your Weber numbers, and you might have atomization. Also, you might have maybe coalescence that forms larger drops again that then have to break up again. But it depends on what you call primary. When do you define the end of primary atomization? When is secondary atomization? When should it start?
Actually, I think it's very relative to the spray you are considering, because my PhD thesis was on the behavior of Canadair. So it was a huge spray. You have 5 square meter cube, 5 meter cube of water atomizing. If you make a Rayleigh-Taylor analysis, you get blobs of several centimeters, and it's impossible to conceive that these blobs of several centimeters are still stable. So they shall destabilize another time, and maybe another time again. So it's dependent on the scale. So it may be important, but I think that it's the more important is to have a good understanding of the physics behind, rather than say it's primary atomization, secondary atomization, ternary atomization. We should more focus on the physics behind than on the vocabulary. But I think that in a code, when you have very small particles and you decide to track them in a Lagrangian way, it's always a good thing to have a secondary atomization model if you want to be closer to the physics.
Yes, I agree. I just sometimes wonder whether we don't force secondary atomization models and the underlying physics that go into the development of these secondary atomization models, whether we don't abuse them to do things in the primary near injector region for which they were not really designed to do, but then we tune them to make them work in this case, which leaves us with a mishmash of 2 different things. And so,
actually, even in experimental, in the experiments, you can see very easily the back breakup mechanism I showed yesterday. Most of the time, you have some rotation, so the bag is not that beautiful as you have some very beautiful picture and image which has been taken, but most of the time it's more complicated than that. So
Yeah,
when you have a model, it's only a model. And
true.
when you put it in your DNS, it's no longer a DNS.
but also the experiment, right, that have these great pictures, it has a circular shaped drop that is suddenly exposed to a high shear. When is that ever going to happen in a real spray? When do you start out with a circular drop? When are you suddenly exposing it to a high-speed shear?
So it's the acceleration part that actually is responsible for the breakup in that experiment, at least. On the IC engine side, is there a perspective of this question to see if in the transient engine, in the real engine, is there a time even for something like this to happen?
I was going to say earlier that if you subject a drop to the Weber number that you encounter, that we think we encounter in the very near field, say within 20, 30 diameters of the spray, diesel spray, it tends to deform significantly. I mean, so we have carried out numerical simulations of these drops in decelerating flows. And now we don't have a breakup model, so we have just carried it to the point where it may break up. But it seems likely that if what you get out of your initial breakup are ligaments, then those ligaments are probably going to break up. So now the question is, as you said, the definition of secondary atomization becomes, right? I mean,
Exactly. So I wouldn't call that ligament breakup secondary, I would call it primary, and that's why I'm saying the result of that has low enough Stokes number, basically, to be picked up and not experience this high relative shear and these high local Weber numbers.
Once it becomes a drop, are there subsequent mechanisms for it break up? Unless there is a cross flow or something, it's unlikely.
Okay, well, I think we'll sort of move on to the next question if I can. Yeah.
Does droplet coalescence also play a role in changing the size?
Anybody, including you.
I don't know. And I say I don't know because we don't have a coalescence model active. So if I just visually inspect how many crossings do I have, they don't seem to be that many crossings, but they might occur on drops that are not fully resolved in the first place, so I can't really say whether it's important. If it is important, yes, you can get bigger drops and you might experience larger Weber numbers and then break up again. So I don't really know. I'd be interested myself.
If I may just add to what I think the way we've done some modeling work in this area using population balances, and the net result of a spray is to break liquid up into drops. So if there is coalescence, it is swimming upstream. And so in that sense, from a modeling perspective, there is two approaches. The magnitude of coalescence is itself going to be small in the sense of being able to measure a change in the distribution. Secondly, the probability of coalescence decreases exponentially as you move away from the nozzle exit because the number density is going down. Where breakup is a single droplet event, single entity event, coalescence requires multiple entities. So from that perspective, I haven't validated this. It is a hypothesis and remains a hypothesis that it's small based on these physical arguments. Just for a sort of a second discussion nucleation question, this is a thought that has been in my mind for a little while. I wanted to actually take advantage of the group's sort of poll the audience lifeline here. When you have evaporation, you have a sudden change in the densities of the phases. So does that also change the atomization characteristics in a way that they sort of feed into each other? Because this is a question that is relevant to the talk that Guillermo just gave about biomedical sprays, as well as it is to any other combusting spray. Has there been any experience where,
Some boiling simulations using some volume of fluid methods. And what we see is that, okay, in boiling you also have some kind of an evaporation happening. So I will just talk about it. So in boiling you have a stabilizing influence because of the heat transfer. That's why you get a mean film thickness there. In case of, so what actually the phenomenon that you're talking about, what happens when evaporation happens is that you have a certain density change, as you said. It's not just density change, it's a sudden change in the volume around it that gives a vapor thrust at the interface. So in the breakup of ligaments, probably when the ligament is also having some evaporation on it, there may be some vapor thrust, basically some impulse that it can give to the ligament, and it can actually lead to a pre-breakup or a kind of breakup before it should have happened without evaporation.
Without evaporation.
Yeah, I think there should be some influence of it.
So I would like to add something. So we have experience from industrial point of view of influence of evaporation on atomization. Typically, when you have multi-component droplets, that means we have made a lot of experimental study, but we couldn't conclude. That means basically the process is for making fiberglass. We're spraying phenolic resin, and it's a mixture of resin, and you add some water to have the liquid is a mixture of water and also of resin, which is liquid. And we have tried several experiments, and in some cases, what happens is you spray it in a hot atmosphere, and you have some kind of micro explosions. Typically here, the evaporation influences the atomization. It's not atomization by the shear or turbulence fluctuation. So typically, we have performed some experiments that we made some. It was made on a test bench by Onerado. That means we have performed some laser diagnostics to see what happens. It was very difficult to conclude because we were looking at the beginning for small droplets because we have made the mixture, put the injector, PDPA, and so on. So we have also put a tracer into the droplet. And we were looking for something small. What happened, we made a probing of the size with PDPA on the axis of the jet, and the size was increasing. So the question was it really coalescence or not? But in fact, we found that there was a growth of the particle due to the vaporization of one component, and then afterwards there was explosion, and that's what we analyzed. We had small particles downstream. So that means when we have multi-component fluids, it can influence strongly the atomization process.
In internal combustion engine sprays, it's unlikely to affect atomization when you consider the time scales of evaporation and breakup times and so on.
Yeah. Yeah.
Related to what Professor Thomas said, like for effect of evaporation, I mainly want to focus for primary breakup, like the formation of ligaments. The necking in India will definitely be affected by temperature, but what I am not sure. I just want to listen your opinions. That I think that the when the ligament is forming, especially in primary atomization, the time scales will be very short period. So will we have enough heat to time to evaporate the evaporation to make an effect on the ligament formation? Like for example, if we are spraying in a quiescent chamber, in a cold flow, or in a heated chamber, so relating only to primary breakup, secondary will definitely be affected. But near to the nozzle, say 5 to 10 diameters, the formation of ligaments will have any major effects because of temperature?
I can't answer this directly, but what I can say, I was involved in some work that's currently done in Aachen from Peng Seng, and we looked at the primary atomizations, the same type of methodology, but we added a evaporation velocity to the interface. And we looked at how does that change the dynamics of the interface, the ligament formation. And it turns out it has quite a substantial impact on the formation, because it acts a little bit like in premix flames. There's something like kinematic restoration, where you have an interface, a corrugated interface, and you propagate it normal to itself. It kind of eats away the corrugations that you have in there. It's called kinematic restoration in premixed flames. And if you add something similar like an evaporation velocity to the interface, it's a pure kinematic thing. It will eat away some of these corrugations that will generate the ligaments down the road. Now it all depends on how strong that velocity is, of course, and these simulations were with an assumed constant velocity to see if there's an impact at all. So yes, it depends, of course, on the details of the heat transfer process, what the actual evaporation velocity at that point is. But I can surely see that if it happens, then the ligament formation process can be either inhibited or the pinching can be accelerated at certain points. It might have a significant impact on the primary atomization.
So what I'm mainly interested to know is like whether that ligament formation effect that will be minor or that will have a major difference with temperature that should be accounted for.
Well, if the temperature is high enough that it has the evaporation velocities we looked at, it has a major impact.
Right.
Now, whether it has that evaporation velocity, whether that was a realistic one, you might have to ask Peng to see whether what he found out in the end. But if it has those values, then it can have a major impact on the atomization characteristics.
Thank you.
Yeah, Achintya.
Actually, I would just like to expand the second question. I mean, since we are talking about temperature effects, how important do you think are the thermocapillary effects on breakup or
That I can almost answer, because the single drop turbulent atomization simulations we did, the point of that was to add temperature fluctuations to it and see whether there is an impact. So from our initial analysis, the thermocapillary, the Marangoni forces that will induce a Marangoni flow field are not important, because the time scales of those are just too long to establish these type of flow patterns inside the drop compared to the actual time it takes to atomize. However, that being said, the local variation of surface tension coefficients due to temperature might have a significant impact. So not necessarily the Marangoni flow that will be induced in static drop, that won't matter, but the local variations in surface tension will significantly impact your local Weber numbers, because you can drop your surface tension coefficients to near zero, right, when you get to boiling. So you'll have very large Weber numbers, and then you might actually go back to secondary atomization, because suddenly your Weber number of that drop is so low that you don't have any surface tension anymore to hold it together. So we think that that has a significant impact. Now, we try to do these simulations with temperature variations on the order you would expect in a turbulent flame field on the same type of scales, and it turns out that your drop sizes have to be somewhat large to get significant enough gradients on the drop, on the scale of the drop, to make an impact. But we think it will have an impact just by modifying the very local Weber number. Not even the drop average Weber number, but the local Weber number on the surface of the drop.
I'm not talking about the drop. I'm talking, say, about the sheet itself in the primary.
Oh, same thing. For ligaments, same type of thing. They're even more.
They're much larger.
Yeah, no, they're even more, because. But then again, it's in that how much. Once you've got the jet established and you had some evaporation to cool the surrounding air there, right? How much temperature fluctuations will you have there? So it's a bit easier to look at a single drop from a more fundamental point of view in this type of temperature environment. How high can you sustain temperatures in the gas near the injector in the primary atomization region over a long time? That plays into here as well.
Okay, well, since we're doing well here, we'll move to the third. This will probably be the last one that we can get to today. But we all have measured drop size. At least the ones that have done experiments have measured drop size distributions. What explanation do we have for drop size distribution? And specifically, the question on my mind is, we looked at diesel injectors to pressure swirl atomizers, gas turbines. All of them have very similar drop size distributions. A log normal, gamma distribution, or some sort of an exponential tail, which to me tells me that the explanation has to be universal, beyond it has to go beyond a particular geometry of an atomizer. I'm just throwing this question out to see what do we think is the physical origin of a drop size distribution in a spray.
I'm not sure it's that universal, because if you are flowing very slowly, you will have a different kind of distribution. If you are flowing very quickly, you may have other kind of distribution. And if you are going very, very quickly, like in a diesel direct injection, you can have thermodynamics effects. If you have thermodynamics effects, it should be different from if you are only instability effect, like in inkjet printer. But in between, I think that there must be a role for turbulence, and I think that, as far as I'm concerned, I've tried to model the effect of turbulence intermittencies on the spray PDF.
When you say turbulence, liquid phase or the gas phase turbulence?
That's an open question. I think that it depends on the kind of injector, but from what I have seen experimentally, even if you have very high turbulence in your liquid phase, you can have also very high turbulence dissipation in the liquid phase. So the turbulence in the liquid phase can be killed out very quickly. So a few diameters, injection diameter after, you have no more turbulence because it's just died because epsilon is quite high. So but there still log normal distribution seems to be related to turbulence, for instance. So there seems still to be some relationship between turbulence and atomization. And on the poster I presented here, and on other kind of pressure swirl atomizer, what we have found is that the average size of the droplets could be related to the Taylor scale, and the smaller size of the droplets can be related to the Kolmogorov scale, roughly speaking. But if you look, the Kolmogorov scale is related to epsilon power -1/4. So if you want to have smaller droplets, but if you want to divide the Kolmogorov scale by 2, you have to increase the turbulence dissipation rates by 16. So it's become very difficult to go under 1 micrometer, actually. That's why most of the time you don't have droplets smaller than 1 micrometer. That's my interpretation.
Okay.
So.
Yeah.
When we say drop size distribution, normally this distribution will account for only spherical particles, right? Whatever we say, distribution of drop size, we normally account for spherical particles, right? But in real spray, we see a lot of non-spherical particles, and the PDPA measurements, if you take it, you see a lot of signals are getting, removed. Actually. Are they really, getting to, if we include it? How do we say that?
Yeah. So the question there is, if you say,
is this whatever we are talking about? Is it real representation of the spray?
At some distance downstream, it has to be a real representation. Maybe an unphysical distance, but after all the process is equilibrated, I can argue that there is a drop size distribution, a spherical drop size distribution. But that may not be a realistic distance to start with.
Based on their volume and area, equivalent diameters.
But for example, if you look at just immediately next to the ligament breakup, you don't see really a spherical particle.
Yeah, they are not
and
spherical.
When we make measurements, these particles are getting eliminated. They are not really considered.
But you are not making measurements where ligaments are present either, right? I mean, at least not with the PDPA. With there are other techniques, but I think your point is certainly well taken. That wherever measurements are being made, there is no universality, and there is no like that. It's still a dynamic situation in that sense. Yes, sir. No, no, I'm done.
I think your question is whether when we are representing the droplet size distribution, we are using on the x-axis, we are using diameter as the coordinate. How appropriate is that? Uh, in that, what I can say is that in some applications, or in some researchers, what they use when they use this population balance or this kind of distributions, they use other internal coordinates. Like some use volume on the on the x-axis. So it's a probability of finding a particle of certain volume, or some people like Mark Masso's group, they use surface area as their as the internal coordinate. I mean, it may not be governed by this reason. I mean, for example, in surface area, that has got some distinct advantages in the numerical method that they use in quadrature method of moments, but it's possible. And in meteorological problems, in raindrop distribution, they routinely use mass or volume of the droplet as the internal coordinate. So I mean, it is possible to look at that way.
I think we're almost at tea time here. So, Marcus, do you want to say anything? Okay, well. Okay, do the fourth one. Okay. Okay, I already pinned the tail on one person here. He's going to start the discussion on this. You know, I myself, my PhD thesis was on linear and nonlinear stability. And I want to, now that I've put on some gray hair, ask, is it really important? Use the mic, Milind, if you don't mind, please.
I think it's a matter of, you know, what kind of information you're looking for, what is the resources you have, how much you're ready to spend to get that information. I think linear instability is useful not to give us, you know, exact values, but to some extent give us some trends by changing, you know, certain parameters. Would I get, you know, would I make that sheet or make that jet more unstable or less unstable, that sort of thing. Now, it does have limitations, especially when you go to, you know, non-Newtonian type of fluids. Sometimes you will get linear stability, which shows that, you know, jet is becoming more unstable, and it turns out that that need not be the case throughout the process, that the disturbance starts first, but, you know, because of variety of viscoelastic effects and so on, the droplets may not actually break up. They might thin out, the jet might thin out and so on. So there are limitations, but it's a quick way of getting some information. So in that sense, it's a still useful tool to some extent.
Yeah.
Actually, I mean, I almost agree with Milind that it gives some rough estimate, but that quick estimate can sometimes be misleading. For example, a very important distinction that we make is, say, if we talk of the two modes of disturbance, sinus and varicose, which one is more dominant? So, I mean, linear stability analysis almost tells us that it's at the kind of conditions that we encounter in atomizers, it's always the sinus mode that dominates. But in one of our recent studies, we found that at certain conditions, it was the varicose mode. I mean, if we consider which one is more dominant dependent on the breakup time as predicted by nonlinear analysis, the results were somewhat different from what we saw from the growth rate predicted by the linear analysis. So, I mean, our confidence is that, I mean, other people have also found out similar things, but to me, that way it's extending it to nonlinear analysis. I mean, I think it's worth.
Is worth it. Do you have?
If I put it, that is, the linear analysis gives the trends very clearly. If you want to study the influence of gas to liquid density ratio, Weber number, or viscous effect, everything, the trends we get from the linear analysis, there is no doubt on that.
But the accuracy, per se, there is a limitation. Maybe the linear analysis may not give you the accurate prediction of the drop size. We cannot get the breakup length. But the influence of all the major parameters can be inferred from linear analysis.
Yeah.
I think that linear instability should not be used to try to predict the spray PDF, but they should not be ruled out either. At the beginning, when I began to work on atomization, I ruled them out because I was just wondering, okay, there is a linear instability threshold, but we are so far away from the threshold. What's the use of this linear instability? But I think that this linear instability governs the large scale of the flow. So it can be useful when you want to make a first-hand analysis with a sheet of paper. If you can use LES, then you will have the large scale. So if you use LES, they are of no use. But if you just have a sheet of paper, it's a good way to have the large scale of the spray.
Gaurav wants to, and then you.
After you. No. So I think in linear stability analysis for atomization, there is an issue of base state, what base state you're going to choose. That's a very important issue because you cannot start with thin, long jet and then you perturb it and then see where it becomes unstable. The base state is always changing, it's evolving. So how to actually incorporate that in your, you have to perturb the base state to get proper results.
Before you answer, I actually have a question for you too. Well, you showed those jet simulations. Is there any correlation to like some of the wavelengths you see there to linear analysis?
Okay, I was just about to say.
Okay.
Okay, so there's two different things, two different senses. One is these injections into stagnant air, so these diesel type things. What we think we see there is imprints of liquid turbulence on the jet surface that provide a source for initial disturbances that then get picked up by instability modes. Now the problem is that these initial disturbances seem to be sufficiently large that you might be outside of the regime of linear stability analysis right there and then. So your initial amplitudes are large enough because of the turbulent flow that you just jump out of that regime. So you would have to go to nonlinear stability analysis, is my thinking at that point. Because even with linear stability analysis, you need initial amplitudes, right? Even if this is one of the wavelengths is your most unstable wavelength, if it's not forced in the initial boundary conditions, right, another wavelength might just win out because it has this larger starting amplitude before you reach the nonlinear regime. So I think turbulence can be the kicker to start off the instability modes. And then when it does, then you might be outside of the regime of linear stability analysis right there and then. Then for the jet and crossflow, we actually did POD analysis on those because you have these dominant wave features you see on the jet on the windward side, which are really predominant traveling waves. And we did POD analysis to find their wavelength and then try to correlate them to either acceleration-driven instability, so Rayleigh-Taylor type instabilities, or shear-driven instabilities, Kevin Helmholtz type instabilities. Typically, it's thought of to be just Rayleigh-Taylor, and that turns out to be very likely true, but because we had very low density ratios, so very high pressure gas, you could think that the aerodynamic instability becomes important again. So long story short, we did this POD analysis, we tried to get the dominant wavelengths, compared that to linear theory, and got maybe the trend right. And in jet and crossflow, it's a mess because you maybe start growing a wave, but then you interact with the crossflow, the jet gets bent, the wave that you get gets stretched out, so what's the wavelength you're looking at? It's not the wavelength of the initial instability anymore, so you get it all stretched out. So you have a mishmash of different effects going on at the same time. So as soon, plus you have turbulence that provide initial disturbances, so anytime you have not these clear-cut, nice cases where you have a single wave that just grows clearly on it with a laminar jet, I'm starting to believe that linear stability analysis will not get us very far except for some qualitative trends, and you would have to go to nonlinear analysis taking the actual flow fields into account. And we tried to do that with the jet and cross. We extracted the mean shear profiles to put them into the full equations to predict. So we went beyond the simple standard linear We went to more complicated ones to try to get agreement. Even if you have the full data, it's very hard to try to extract again. Is it Rayleigh-Taylor? Is it Kelvin-Helmholtz? We have some indications that it is Rayleigh-Taylor predominantly for high density ratios and maybe Kelvin-Helmholtz for low, but it's all qualitative. And I have some doubt whether that's usable in a primary atomization model to actually predict what the outcome would be, and not just the other way around.
Part of the motivation, at least for question number 1 and 4, is because most CFD codes like Fluent have models in there. They're just a radio button click away from using. Okay, and so like for example, the tab model, which was
again, the way to approach that might be to take partial solutions. Maybe what Marcus is doing currently might not be giving the full picture, but on the other hand, it might be providing picture which is suggesting that some of the things that you're doing in your applied work is not correct. So then that needs to be changed. And then you need to compare with experiments. But if we start by saying, well, what I have today already predicts everything, then of course there is no room for making that kind of a adjustment, right, along the way. And so.
Okay, I think we're about 15 minutes over time, which is usually a good point to stop the discussion. Okay, thank you very much. We have a talk by Sujit following this, and then tea. I was wrong earlier in saying that we're going to break for tea right away here. Our schedule says we break for tea at 3:30, so.